This program is brought to you by Stanford University. Please visit us at stanford.edu.
What we haven't talked about yet is the real building blocks of life, chemistry. And as I mentioned last week, chemistry has never been my forte because I think it's taught in such a static, boring way in general, and I apologize to the chemistry aficionados in the room. But when I started to learn about Lou's work, it suddenly changed in my mind. I wish I'd learned about it when I was at your stage, because chemistry is much more than a static textbook and a way to weed out pre-meds. It's something that's really alive in a way like biology. Chemistry had a beginning. Molecules have an end, and they have a distribution in space. And this is the sort of thing that Lou's going to talk to us about today. Over the last 25 years, Dr. Alamandola's research has revolutionized our understanding of interstellar molecules and carbon-rich dust. You're good.
Okay. It's always fun to be here, and interesting. Every year the class gets larger and larger, so Lynn's doing something right. The future's in good hands. You wonder sometimes with all that's going on. The excitement of the field keeps growing. And what I'm going to try to give you fit into this progression of the class, what you've heard last week and where you're going. Is there anything next?
Yeah. He's coming first.
So this basically sets the stage. This is the background. This is that awful chemistry, which really isn't so bad. In fact, we're all here thanks to chemistry. We wouldn't be around, and most of the world as we know it wouldn't. Chemists are very clever. Anyway, from astrochemistry to astrobiology, yesterday, today, and tomorrow. We've made a lot of progress over the last few years, but I really want to give a background and put this whole talk in context. And what I want to come back at the end is where we weren't not that long ago, some 30, 40 years ago. Is this about the right sound level?
Don't you have a mic on you?
Yes.
Yeah, he's doing it in the back. I'm just doing the video.
Okay. All right, so we'll start with yesterday, and I want to give everybody a little context. Interstellar chemistry was non-existent in our thoughts and the minds of people until the 1960s and 1970s. In the background, in the past, space was very barren. It was thought to be very barren, high levels of radiation, no compounds. When I was in high school, and although I didn't know it, and a lot of the things I'll be talking about today probably happened when you were in high school or perhaps grammar school and you didn't know it, but there's been a steady drumbeat of progress. In the early 60s, OH was discovered. Now, that's not a big deal. For those of you who've had chemistry, it's a simple diatomic molecule, two things. It was so exciting and so shocking. It was on the front of the New York Times. It made the headlines in Time magazine. This was a real revolutionary change in our understanding of how we fit in and how, organic chemistry was thought to take place certainly on other planets if it existed, if they were there, but the level of complexity would be most rich here on this planet. Well, over the next few years, OH, ammonia and H3, H2CO, there's formaldehyde, carbon monoxide, they were discovered. You can see for yourself, 68 to 70. In fact, the discovery of formaldehyde was so exciting and surprising, the conclusion of the paper, can you imagine this today? Polyatomic molecules containing at least two atoms, other than hydrogen, can form in the interstellar medium. So this kind of puts the mindset of where the human race had gotten to at that point. Well, about the same time, infrared astronomy was just being developed, and infrared astronomers discovered, to their surprise, in a little emission band at 11.3 microns. And for those of you who have done any spectroscopy, what would be expected in a region where there are simple molecules like this, or atoms, is the lines would be razor sharp. This thing was fat, squat, very peculiar place, and it was suggestive It was found of the many objects it was found right here. The edge in the Orion Nebula. The hot stars are up here. This is a place where stars have been formed in the giant molecular cloud that's around Orion. This is the cavity where the stars are formed. They're blowing all the dust and gas out of the edge, but here's the part that's resisting it, slowly eating away. And it's at these kinds of interfaces that this feature was found. And you can see this is dusty. People that, oh, it's not a sharp line, not a gas phase thing, that's probably a handle on the dust. It's the first time we can ever understand what the dust is made of. And it's a carbonate, it's a classic carbonate band, just like chalk you use, still use blackboards here. CO3. But the way to test it was to look for the other infrared bands coming out of carbonate. And we were fortunate at Ames in the day to have an airplane that would fly above the water in the atmosphere. You couldn't get at this from the ground because water absorbed the key features. And there was a prediction that there would be a very strong band at 1,400 wave numbers. Now, astronomers and chemists never talk the same language, and that's why half of the confusion arises. Astronomers talk microns, chemists wave numbers, but chemists have been doing it for a lot longer, and it's a lot more refined. But we'll get back to microns.
So I don't have you at the same time.
Well, my old boss in Berkeley said, the biggest impediment to infrared astronomy infrared chemistry half a century ago was the micron. It's just not a physical, it's a wavelength. There's no energy to it. Anyway, nature being nature, the divine sense of humor, the band was predicted at 1,400 wave numbers, no band, no big monster. Then we got a twofer, one about here, about 1,300, one at 1,600, or for the micron folks, 8 microns, 6.2. So this sent everybody back. A few of us being chemists actually have friends in the oil industry, and I was talking to some of my friends, and they said, that sounds an awful lot like the spectrum of soot. So, and oil folks know their soot, and sure enough, this was a phone conversation. I looked at the paper, and I passed out when I saw that. That's a really close match. And that was the start of something big, and you'll see by the end it's really revolutionized. It's one of these little things no one would have thought of soot in 1973. Forget about it. And that's how the game is played. And so, again, you call the oil folks, they know their soot. What's soot made of? Soot is something like this. If someone has a laser pointer, or is there a stick? I could use a like this a lot easier. Thank you. Good. Here's a soot particle, black, on the order of 100 nanometers. What is soot made of? It's mostly carbon and hydrogen. There are a few other impurities in it, but since you're putting gasoline in a gas engine, what's going to come out? The black stuff are these kinds of things. And what they are made of are these aromatic networks, and we'll talk about that in a moment. They also have smaller molecules. These are the in clusters, and then finally we come to these things called polycyclic aromatic hydrocarbons. They're chicken wire-shaped molecules. Each one of these black dots is a carbon atom. In this particular form, it forms a flat hexagonal network. The edges are decorated with hydrogen atoms. And why are they called polycyclic aromatic hydrocarbons? Diesel is not very exhaust is not very aromatic, but we have to go back now a century or so, a century and a half. Polycyclic, we can all see many rings. Aromatic, this is the kind of structural chemical unit that's found in a lot of flowers, perfumes, and so on. So the chemists in the late 1700s and early 1800s were starting to unravel in the 1800s. They came across these kinds of structures, and they became classified as an aromatic grouping. Hydrocarbons, it's simply because they're made up of hydrogen and carbon. So now I want to give a little demonstration, and I think it'll work a little bit, on how do astronomers tackle these things, track these things in space. And let's just see, let's imagine, and I'm going to give a demonstration in the visible, a little fluorescence demonstration. Astronomers track these things in the infrared. This is a UV lamp. It's not bad. It's the day glow kind of posters, if some of you have seen. And I'm not sure, you see how I can bring it up here? you're not seeing much of the light. It's not.
You can't see, come on down.
You're not reflecting the light. These are little toys from Toys R Us. But let's imagine the star is here. This is a little bottle of a PAH. Now, out there in space, it's floating around. You wouldn't see it, but in the vicinity of a starlight, they start to light up. And I don't know how can you see this thing. These things are great fluorescents. And those of you who watch crime shows on TV see this. It's all set up, but a lot of these molecules have this property. And check out this tide box. I mean, can you all see this? It's just, it's like lighting by itself. So these molecules have this wonderful, wonderful property of fluorescence. They also do infrared, but stars give out tons of light, they're visible. So they'll, if you turn the lights on, none of these things will all become invisible. But not so with the infrared. This technique is also now we're working on, just as an aside, using these as developing tools to track the distribution of these kinds of organics, let's say on Mars or the Moon or whatever, or in these icy planets. We're trying to figure out a way by just stowing a little UV lamp when the sun sets or whatever, or near a dark shadowed crater, just simply turning on a UV lamp, anything that's exposed should start to light up, and that'll be additional important information as to where to look next. But let's get back to deep space. So here we are in space. It'll take a second. Okay. The UV photon comes in, the molecule gets excited. It cannot emit in the visible because of the conditions in space, and that's a whole other series of classes. We won't go there. And it spits out an infrared photon. We now know the spectroscopy of these PAHs very well. We didn't know any of this at the beginning, in the 70s and 80s. In the nice 11 age, people worked very hard. We understand the infrared spectrum very well. And this is what it looks like. On the bottom is the spectrum from Orion, that same place I pointed at with my finger in the Orion Nebula. Each one of these bands, you see how this is the 11.3 micron band that was discovered. It was very weak when it was found because the techniques were not so clear. Here are the razor sharp bands I was talking about. So it was clearly very different at the time. Here were the surprises, the expectation if it was carbonate would be something here. And this character out here, 3 microns. So now here's what's causing these particular bands. The little molecule is vibrating. This carbon hydrogens are stretching. Carbon is a little bit more negative than the hydrogen, so it's an oscillating dipole moment. The nature of the vibration says it's oscillating at a frequency that falls in the infrared, and it falls at precisely this frequency. This is the carbon stretching. You can see the carbons are stretching separately from the bending hydrogens. And this broader feature here, this is the carbon-carbon stretch. This is the combination of everything. And the one out there in the right field is bending out of the plane. These all have unique frequencies, and you cannot look at any one of these and say, oh, that's a PAH, or that's a gasoline, or that's a carbonate, or that's uranium chloride. But taken together, it's really a signature. It's a recognized pattern. And as I said, chemists have been using this for a long time to characterize compounds, and we have that wonderful resource to look into when astronomers walked in and invented infrared astrospectroscopy. There was a lot of information. So now, that's yesterday. That's probably 20, 30 years worth of time. That sets the stage. And now I'm going to shift. Remember this later on. Keep it in mind. But we're going to shift now. And I'm going to put the PAHs with ICES and find out that chemistry is really amazing. This is a picture of a galaxy taken with the Spitzer Space Telescope. It's an infrared telescope. As the pH ideas developed and the capabilities increased, people the Europeans, and then we launched infrared satellites, which were capable of taking pictures of the sky, not just one little pencil beam, but the whole enormously wide object spread out in entire galaxies. This is a spiral galaxy similar in shape to what we think the Milky Way is, and if this was the Milky Way, presumably it would be somewhere out here. What they did on this satellite is they put a filter for that very strong band, that 7.7 microns, that strong PAH feature, to track the distribution of PAHs in space. So what you're seeing is not a visible picture of this galaxy. This is what the Spitzer telescope tells you is the infrared emission from this galaxy. And the red filter tells you the distribution of the PAHs. This is a stunning picture. They are all over. They are the most abundant organic material in the universe. They are small, molecular in size, so they are accessible chemically. They can do all sorts of nice things, and we'll hear about that later. So just like I showed here with this fluorescence, astronomers use infrared fluorescence to trace the distribution of this stuff. And here's another doozy. And this one, this is Sombrero Galaxy. Many of you probably have seen this picture years and years ago. And this is in the visible. In the infrared, using the same filters I just described, this is where the PAHs are. They just look like one of those flat types of frisbees. Now, if you keep going back and forth in your mind's eye, you'll see this disk is inside this dark lane. The stars, the brightest and most intense radiation is here in the center coming out. And this thing, the PAHs are all lighting up on the inside, right alongside this dark dust lane. And this is the composite picture. And you see again, it's dark, that's not reddish. But just where the starlight hits the edge of the disk, it's very bright with PAHs. So I'm going to take a pause now and summarize what the PAHs have told us and why they're important for astrobiology. And then we'll move on and get into some of the evolutionary chemistry. They're critical to astrobiology. As I said, they're very abundant, they're widespread, and they're chemically accessible. It's not like a chunk of coal you can kick around. These are little molecules. You can ingest them. They're nano-sized particles that can get into biochemical systems. In fact, they're very carcinogenic for that reason. And once they're out in the atmosphere, pHs by themselves are not bad, but they start to react with them. So grab an OH, put an NO2 or something like that on them. Then if they get into your system, DNA, they'll grab onto one of the bits of your DNA, and they'll become mutagenic. And some of the strongest carcinogens known are in this family of compounds. So they're good and bad. They're more abundant than all other known interstellar polyatomic molecules combined. This was a hard pill for a lot of interstellar chemists to accept, but it's really true. So carbon monoxide is not a polyatomic. It's all over the place. These things, as a class, are almost as abundant. So it's really stunning. We know these numbers are larger. They probably contain 20 to 30% of all the cosmic carbon available. They are also found in meteorites and delivered to the Earth from extraterrestrial interplanetary dust particles that rain down on the Earth every day. Some 30 tons of these things fall every few months. So part of the dust right here on the floor probably contains some of these tiny little particles which have pHs in them. The other surprise, the Spitzer Space Telescope is unprecedentedly sensitive. And what they found is this PAH emission only a few billion years after the Big Bang. Redshifts of, I think it's up to 6 now. Now, 20 years ago, all astrophysical models, it took a long time for heavier elements to be produced in a universe that was primarily made of hydrogen and helium. Now they're inventing new stars, heavy, super heavy, massive stars, right after the Big Bang, right after a few billion years, to generate enough of this carbon quickly. So carbon's been around a long time, a lot longer than we had supposed. So that's a big surprise. Lots of surprises here. So now let's shift. What we've talked about is the emission from the PAHs are at the skins of these dark clouds, or this, this is a diffuse medium UV light from the stars is impacting the edge of these dark things. This is where you see a lot of the PAH emission, right at the skins, and sometimes from embedded stars. So if you point your telescope along here, you'll see that emission spectrum. However, the real question now, and certainly important for us from this class's perspective, is what's going on in these dark clouds. It's because it's in these clouds that stars and planets are forming, and presumably the nice, pleasant place we're on had a history like this way, way back. So astronomers, again, in the 60s and 70s tried to map some of these things, trying to find infrared hotspots so they could train their telescopes, either earthbound in the air or in satellites, and measure the spectrum of the intervening material. So imagine the star either behind the cloud or in the cloud heating a region, generating an infrared source. Infrared is because we perceive it as heat. And that source will generate a black body spectrum in all directions, and if we pick up a little bit of a line going through a cloud, the material will superimpose absorptions that indicate what kind of material is present. So imagine the star has kind of a smooth infrared background, and as the light passes through the cloud, bits of the light are taken out. So this is an absorption spectrum compared to the emission we just talked about. And so basically, what we try to do in our lab, and this would just be a short diversion, we try to duplicate the relevant conditions. We can't make black holes and we can't make super hot plasmas, but we can create the conditions that duplicate the conditions molecules feel themselves in when they're in these different environments. So what you've seen is some of the hottest regions. The pH emission comes from places like this where there's a star, really exciting local gas. This is a visible picture of what's called the Horsehead Nebula. If you looked at this in the pH features, you'd hardly see the head sticking up. There's just a sea of high emission all around here. But then the question is what's going on inside, which is it's really very cold in there, almost absolute zero, almost 500 below 0 Fahrenheit, or 10 Kelvin, 10 to 20 Kelvin. So we want to find out what happens when we go into these dark regions. As I said, the reason for this class is because this is where stars and planets are formed. So this is the top of the Horsehead close-up, a nice little picture. If you looked at it in the filter from the Spitzer Space Telescope, this would all be glowing in pHs. But if you measure the spectrum with a slit going down, the pHs are very bright here, especially right along the edge, and then they get dimmer and dimmer and dimmer, and finally they go out. What's going on in there? Now, what you can do is you see some of these little red spots. These are embedded stars or stars behind it. And there are others which you could not see at all that are really darkly embedded, but in the infrared, they're boomers. So astronomers train their telescopes on these things. And here's the cycle we are fitting ourselves into. I talked about star and planet formation. This is what's happening. We're now in a dense, dark molecular cloud. The material, the astronomers use the word dense. It's really not dense by terrestrial standards. One of these tiny dust particles that gives it the look of a cloud would fill a volume maybe the size of this room. It's just the scales are vast. That Horsehead is something like 60 light years from back to front. So you're just looking through lots of stuff. So there's a dust particle here, there's 1, 2 miles away, and on. But you're looking through lots of miles, and so eventually it blackens up. So we're starting here. Something disturbs it. A couple of particles come together. They stick, they get bigger, this goes on. And these clouds last some 10 billion years or so. Eventually, there's enough of a gravitational attraction that even the gas gets pulled in, and the mass gets enormous once you have reach a critical mass, and this is sucking in a lot of hydrogen. You'll get a thermonuclear reaction going on in the center, driven by the gravitational forces that ignites a star. The stuff that's not sucked into the star orbits it. The angular momentum of the rainfall gets twisted around, and you'll get a planetary forming disk. Low mass star is formed. The cloud starts to break up into planetesimals. These are basically seeds for planets. Then eventually, this is all dispersed, the cloud is gone, and you're left with a nice planetary system, a solar system like ours, and these last for quite some time. Eventually, the star burns up all of its hydrogen and making heavier elements, and it becomes a red giant. It swells to enormous scales, and it swallows up the inner planets, and it starts to throw out heavier elements, carbon, nitrogen, oxygen, and so on. These float around in the diffuse medium, and this is where we see the PAHs and a lot of those types of things. And so it continues. And the universe is slowly enriched in heavier and heavier things. So you say, how in heaven's name can we understand any of the chemistry and things like this that are so far away? Well, there are two things that work in our favor. For those who've had chemistry will appreciate this. This is the astronomer's periodic table. It's much, much, much simpler than the thing you have to struggle with in chemistry class. Most of the universe today is hydrogen, and the area of each of these boxes is in proportion to its relative amounts. Helium there's lots of that. These are all leftovers from the Big Bang. All of these other things were thought to be formed in the stellar evolutionary cycle I was talking about. Well, hydrogen's interesting, but it can only make H2, so we don't care about it. It's nice, it's good. Physicists love it. They study it to death. I'm sure they'll study it forever. Helium that bounces around, it's like a marble, doesn't do much. Here's when the chemistry gets interesting. Carbon, nitrogen, and oxygen. And neon's another inert gas. So these are the main players. So when you're restricting yourself to this kind of chemistry and spectroscopy, as we see in a minute, it gets a lot simpler. So now, I also like to make a point here about life. You've seen lots of these science fiction movies where there are silicon rock monsters and stuff. Well, silicon's down here, not much of it. Yes, there's a lot here because of the thermodynamics of it. But on this planet, we have volcanoes, we have lava flows, we have all sorts of things. And as far as we know, there's really no life involving a lot of silicon. So odds are life in the universe is really going to be involving these characters. And with these playing trace roles. Iron, of course, is important, magnesium, flowers, animals, and so on. The other two...
Can I also bring up a point? Isn't it true that you don't see much silicon chemistry, polysilicates and so on in space? So that it was I mentioned in class last week. So the language that we see, the interesting chemistry, is the carbon base, not the silicon base.
Yes. When I was taking chemistry back in the day, this was before silicates were really explored. And it was thought that there was going to be a silicon chemistry very much like a carbon chemistry. In terms of products, we have all sorts of things. We'd be burning silicon in cars, silicon like gasoline. And it just never happens, the chemical properties, even though it's just one row down in the periodic chart. The properties are different enough. So it's another character. The other thing that's allowed us to make headway here is infrared astronomy. This is the picture of the constellation of Orion, the 3 belt stars, the legs and the arms. The great nebula we saw in that second or third slide is down here at the tip of the sword. The horse head is here by the left belt star. In the infrared, this is what that region looks like. It's blocked out the starlight, the bright stars. And it looks like this because of all of the dust. It's cold. It's 100 degrees Kelvin, 150. And that's why satellites here on Earth, in order to detect this, have to be colder. We have to use liquid helium, liquid hydrogen, whatever, to cool the detectors, so that this radiation hits that detector, it gets hotter, something happened. But so when we call these a cold, dark molecular cloud, it's still going in the infrared, but very long wavelengths. So the place is just, there's dust everywhere, and the reason you can see these stars is because these are foreground stars. This cloud is behind this constellation. It's hard to get a three-dimensional picture. So with those two things, the abundance and the infrared, you can start to use IR spectroscopy. Here again, now we're back to microns, 2.5, 3 microns out to 20, and it's in this region that everything that has carbon, nitrogen, oxygen, and hydrogen can either emit or absorb. Anything that has a carbon-hydrogen bond or nitrogen-hydrogen bond, ammonia, water, OH, will absorb or emit in this region around 3 microns. And so you say, okay, well, what good is that? We have a band there, just like we did with the PAHs. We saw a CH stretch, but we didn't know it was a CH stretch. Maybe it was an OH. Well, then you need to look at the rest of the spectrum. The CC stretch is full here, the CO is full there, and so on. And then you get these out-of-plane bands. So when you put the pieces together, you can start to classify the chemistry. What kinds of things are out there? And of course, since the atmosphere is full of water and CO2, it's blocked from the ground. So we have to go up in airplanes or satellites to get access to this information. But we live in an amazing time, and this has been done at a number of places now. There are about 5 or 6 labs in the world that provide this kind of data, and there are observatories all around the world. So let's go back to 1976. What was one of these? The interstellar dust grain model. We just heard about dust a little while ago. Not that long ago, inside the cold, dense clouds, the dust particles were cold, small, 0.05 microns, the size of smoke when someone's smoking a cigarette. That's about the size of the particles these that are floating around out there. They're very cold because they're blocked inside the cloud from the background radiation. And so any atoms or molecules in the area will that hit them, even though it might take 1,000,000 years, will stick. Just like water sticks to windows in Montana. So you'll get what's called an ice mantle. This was all well and good, and that was the theory, until the advent of this field and these kinds of capabilities all came together. Very interdisciplinary. And what we do is we try to simulate that ice in the laboratory. As I said, we don't create everything. Groups in Paris, in Leiden in the Netherlands, and now in Japan as well, do these kinds of experiments. And the way it works is this is a little chamber. It's about 4 inches on the side. And here's a cartoon of it over here. We evacuate the chamber. In the center, there's a cold window, and that's this reddish thing here. It's cooled down by a refrigerator to 10 Kelvin. We'll shoot gases in, water, methanol, ammonia, whatever we think will match, and then we find out this is good, no, this is bad, but we'll squirt gas in, and this is the injection port here schematically, and it forms an ice. We'll make the ice just as thick as we think the ice is out there. We can measure this, we can turn this window, pass the infrared beam to it, so just like there's an infrared source, goes through the dark cloud and the ice, and then is measured in the telescope. In the lab, we have an infrared source, goes through the ice into a detector, we measure the spectrum. So we can compare the spectrum in the lab with the spectrum from the telescope, and when they match, we say, aha, we're getting close. If they don't match, this can't be it. And once we've done that, after we've laid the things down, we'll also then dose them with radiation. You can turn the window again here. Here's a hydrogen lamp, which simulates the stellar radiation field, the interstellar radiation field. That's symbolized here by this little red thing. And cook the sample, rotate it again, and measure the spectrum, and watch the chemical evolution taking place. So the way this has been done, here's again the familiar picture now. We have the source, goes through the ices, we measure the spectrum, and here's the real spectrum. The light is, the battery's moved. The real spectrum from that particular star is shown up here. You see it's the smooth black body on the top. The divots are the intervening materials. There is some silicate dust. That's the core that the ices are freezing on. And what you see in any of these 3 diagrams, the dotted lines here, the data points, are measured at the telescopes, and these are the interstellar features. In that case up there, that was measured with the Airborne Observatory. The dots are the data. The solid smooth lines are the lines measured in the laboratory. And when you get a match like this, where the line from the lab fits very well the line measured in space, we think, well, this is probably something like that. And we find water is always very important. Well, this too has come a long way. And this was a spectrum measured by the European Infrared Space Observatory in the this came out in 96. And you can see now that whole spectrum, instead of mysterious bumps and wiggles, pretty much everyone is now identified on the basis of these kinds of experiments. And what we now know is the ices out there in space, miraculously thousands of light years away, are mostly made of water ice. Some carbon monoxide is frozen in, carbon dioxide, methane, ammonia, methanol. And it's remarkable that this was understood some 10, 15 years ago, and we still don't really understand what comets are made of. We know they're icy, but we don't know what the compositions are. This is all inferred from what's coming out in the gas. So they're arguing backwards. But it's beginning to look like there's a similar composition. And so that bears on the idea of these are the primordial ingredients that seeded an early planet. The interstellar dust that's not sucked into that star-forming process, some of them will be captured in that disk. Some of them will form comets, and these are the comets that then seed an early planet. And so these kinds of compounds, this kind of material, may very, very well be an important part of the early chemistry on any planet. So not only, though, is it just simply this ice composition, there's also a lot of ultraviolet inside these clouds. Here is an artist's conception of a star formation, star and planet formation. The star is now ignited in the middle, but all the debris that's been collecting, that's not getting sucked into the star, that will eventually become the planets, and comets and so on, are orbiting around. But the rest of the cloud is bathed with that UV light. So the inside clouds is also some ultraviolet. There are cosmic rays, and they can drive the chemistry. And now with finer tuning, astronomers are starting to see this whole skin is lighting up with the PAHs. So they're all intimately mixed. So what happens when you take an ice and you irradiate it? So this again is that kind of experiment. Now we're looking at a real sample. It's now not on a window, but on a little aluminum block. This is after irradiation, but before that was just like a nice white snowy mountain, little peak. We irradiate it with the UV lamp, this interstellar radiation lamp, and we get this beautiful blue color. Where's that coming from? Just like if you get sunburned, the UV light starts to wreck the chemistry in your skin. If you take too much of it, you'll get hurt. Well, let's say carbon monoxide, that ice that we just saw was mostly water with some carbon monoxide. Carbon monoxide is very reactive. It's also very abundant in space, and it reacts and gives a very rich chemistry by simply mixing it with water, methanol, ammonia, and CO, a very common species out there. So take CO, let's imagine you have water and CO, irradiated up on the right side, the hydrogen atom from the tearing of the water molecule makes the radical HCO. We can add an OH, you'll get HOCO. So, and you see the game that we're playing. The other photo products, and if you tear methane apart, you'll get CH3. CH3 and HCO makes formic acid aldehyde. Another hydrogen addition, you'll get formaldehyde. So you'll see you're starting to get a lot of simple organic molecules, but we're a lot more complicated already than simply water and CO. All we've done is frozen this stuff, irradiated with UV, and we've just got a little organic chemistry experiment going, and the complexity gets stronger and stronger. You can imagine now at the end of this experiment, you warm the ice up, so the simple species evaporate, and we'll analyze what's left. That's how you get to a list like this. But you also find what's left on the cold window or on the cold block is this oily, gooey stuff, this residue. So even though we've started with something that couldn't be simpler, mostly water, there's the ratio, 100 to 50 methanol, CO, and ammonia 1:1. This is the mixture that reproduces that interstellar ice spectrum very, very well. So this is a very good simulation of what's going on out there, and probably going on in comets and maybe icy planets as well. You irradiate it, there are chemical driving forces produce this stuff, and you say, who cares? Well, this is kind of like these tholins you were hearing about a little while ago, but this is made in a very different way. It's not made by sparking, and it's a whole different Cycle.
We could sort of say you're the Stanley Miller of the interstellar
Well,
chemistry.
yeah, I don't know.
If you don't mind, we're going to take about a 2-minute break just so that people can stretch, and
Okay.
then they'll be fresh for the last part of your lecture.
Okay, so
Fair enough?
let me get to 2 more slides.
Okay.
Because then we go to astrobiology. Okay, so what's in this stuff? We can turn the lights on too. We know that when you warm it up to 200 Kelvin, we're getting these kinds of structures. Any of you who've looked at a biochemistry book say, oh, this looks interesting. It's obviously, we've gone from simple water and ammonia, the window cleaning material, to something prebiotically interesting. Up at room temperature in that organic goo, we get some of these large things. We're making ring systems with nitrogen, polymers, all kinds of things. So the picture that we now have, and this is where we'll stop for a little bit, of interstellar dust is this dust, the grains are floating around in space, an ice mantle accumulates on those. Ultraviolet radiation starts to drive the chemistry in those ice mantles, and not only are complex new molecules formed, but also very complicated organic mixtures that remain at room temperature. And this is where we move from interstellar astrochemistry to astrobiology. Let's take a break.
Good. Okay, just stretch for a second. It's really fun having all this, all this dust talk. Greg Laughlin, when he talks about the origin of solar systems, usually gives his dust bunny model where he says it's sort of like all these dust bunnies that form under your beds. But he must think that all of you have vacuum cleaners now. So I just realized, this theme, maybe we should start calling this class from dust to dust or something. We stretch.
Should we turn the lights on? That might help.
I want to make sure everyone's awake for the last part of this.
Yeah, then
Good time. If anyone has a specific question.
Are the lights up front?
With those Aero Astro people, they can go hour after hour without standing up. They're amazing.
don't you guys want some lights on back there?
They're stunned by this. I mean, it really is stunning stuff.
Yeah, it's good to be awake when you're hearing it.
My recollection is you get hydrogen, helium, and a tiny bit of lithium from the Big Bang. Is that correct?
A little bit of deuterium too. All the deuterium now, there's no other way to make deuterium even in stuff. So the deuterium that's out there now, or you're heading toward that.
Wow.
It's a funny story.
I mean, I think that being an evolutionary biologist, it's able to think of chemistry as being meaningless like Big Bang. X number of years before you even talk about protons and electrons.
But this one, when there's a meeting on astrochemistry or chemistry meeting, they always start with the Big Bang. The rooms are packed with chemists. They really don't love this stuff. The first 2 or 3 things, the Big Bang, the first coffee break, they're gone. And that's it. I mean, it gets interesting, but they just, physicists love this stuff. They just keep, yeah, now they're, nowadays we know more about. That's not true. It's not this way. Oh, no, that's my wife is saying the same thing.
Okay. Yeah, everyone stretched? Okay, good. It gives me a chance. I almost forgot. There were 2 atoms walking down the street, and one said, oops, I think I lost an electron. The other one said, how do you know? He said, I'm positive. So I've been waiting for 3 lectures.
Hard for me to beat that, so good, I'm safe, thank you. Okay, so, can we see this okay, or is this now too much light on? Let me see what happens.
There's a dimmer. You can also make it at any level of dimness from that.
This is it.
That's good.
Well, let me know if, dark rooms and I get sleepy. I'm not younger than you are, but. All right, so this is where we were. What's going on in here? Well, the amount of material, what you saw on that little goopy thing was milligrams. It's not enough to do real chemistry. You can't put it in test tubes, shake it, separate it. There are hundreds of compounds, from mass spectral analyses. But we have also been working with people in biochem departments who are interested in astrochemistry, but more within the solar system. And they've been studying meteorites for a long time, and they use heavy-handed methods. They don't really care what the particular compound is, but there are ways to extract things to find out what behaviors the chemicals exhibit. So what Dave Deamer at Santa Cruz did is he took some of our little brown tarry stuff, put it in water, and looked at it under a microscope. And this is what he found. All by itself, as you just watch, something comes out of that tarry material, and slowly these little vesicles are formed. This is very complex chemical behavior. It's not like being at an Italian restaurant and shaking the oil in vinegar and seeing all the droplets. You just leave it by itself. It's a chemical driving force. It turns out what these things are called amphiphilic molecules. They have a polar end and a non-polar end, just like soap. So the non-polar bits, the polar end gets it dissolved in water and it floats around. The non-polar ends are also waggling around. They hit each other, they stick, and eventually this forms a micelle if it's the right size. These are not micelles, but these are little vesicles. Every living thing we know of, every cell, has a membrane made of these kinds of molecules. Think about it. We start with water, methanol, ammonia, and CO. The stuff we know is all over. And all of those dark, scary-looking clouds, the Horsehead Nebula, the Tarantula Nebula, all of them. They're thousands of light years away, across hundreds of light years away. That's where stars and planets are formed. And the natural chemical driving force makes molecules like this in those ices under the most harsh conditions. Well, it gets better. If you turn the lights off, you use a UV lamp like the one I showed earlier, these things glow in the dark. If you notice, this is the same field, these three, and so on. So we've gone again from this very simple mixture to to chemicals that are necessary to make vesicles, and they're also able to harvest energy. This is not life, but these are two important processes of life. The cell walls are important, cell membranes, I should say, are important to separate chemistry inside from the chemistry outside. You need to transport things across that wall, feed what's going on inside with energy, get rid of waste products. But this also can take the energy from the outside, and because it's fluorescence, it can get rid of the stuff it doesn't need, so it can drive the chemistry without wrecking itself. So these are very, if this was a living system, you'd say, well, this could be sort of a simple metabolism, and this is establishing its own identity. Well, Dave Deamer also, as I said, he was working on stuff for meteorites. Here's what he pulls out of meteorites. Here's what he pulled out of our residues. Similar stuff. And one of the questions, of course, is where do these things come from in meteorites? So now there's a whole little cottage industry wondering if this ice chemistry is really much more important than previously thought in determining what's in all of these extraterrestrial rocks and so on that are delivered to the Earth. Because there's really no viable mechanism to form these things. Now, let's remember those, go back to these polycyclic aromatic hydrocarbons. What happens if we include those and make the mixture a lot more complicated? Water, methanol, ammonia, CO, and the PAH. We know they're all over. We know they freeze out in the clouds. Here's what happens. Starting with naphthalene, the two rings, just like this. Simple, couldn't be simpler. In water ice, we make that stuff on the right. It's called juglone. You said, oh, that's nice. And again, this was a very sensitive technique with Professor Richard Zare's lab here at Stanford. They can take 5 molecules and detect them. So we're able to make these kind of identifications now very well. This is this compound is actually used in living systems today. This is in walnuts and walnut and pecan shell biochem. Here, if we start with 3 rings, we'll get this character, and this is an aloe. So all of a sudden, the chemistry is starting to look remarkably intriguing from a prebiotic or maybe even a biogenic perspective. These molecules are very important in living systems because they sit in the membranes, some of them do, and they help transport electrons either inside, outside, or outside, inside. They're also, this one on top is fundamental for many forms of vitamin K. And we're doing this completely abiotically. And of course the question, well, what about amino acids? Well, we worked harder, and sure enough, amino acids are formed. Here we have a blank, nothing on the window. You go through the whole analysis protocol, you see nothing. Here they deposited maps. Jason deposited the ice, but did not irradiate it. Let the thing warm up, very little detection. There's always some contamination because amino acids are all over. Finally, the real McCoy experiment, and they found glycine, serine, alanine. So, to summarize all of these results, in these interstellar cosmic ice simulations, we make a host or raft of compounds that are important in biochemically interesting. Amino acids, sugar precursors, simple single ring systems with 2 nitrogen atoms. Those who know your biochemistry know these are the nucleic acids kind of things, which are DNA. And acids that are used to drive energy reactions. So it's kind of remarkable that in the most basic primitive system, you'll get this array of chemicals that are, those of you who have heard about the RNA world, everything is here. Everything is there inside a little ice grain, inside a little comet. It doesn't have to be one molecule in an ocean moving around, finding another one. So now the thought starts to occur to people, perhaps this kind of interstellar chemistry is playing a role in the primordial chemistry on habitable planets. And you'd say, well, this is such a small input. That's true, but as I said, these things are all close together, and we really are just starting to scratch the surface. Nobody really knows what's going on in these ices. The amounts are too small, but it's already been a remarkable journey, and who knows where it's going to end. I would not be surprised in a few years if we find in comets things that are far more advanced than we ever expected. But this is the picture. There's that life cycle, a stellar death that generates organic PAHs. The material floats around in the diffuse medium, forms a dense cloud, and planets and stars form within the cloud, and that material seeds some of these planets. It's an interesting idea. Why is it even worth thinking about? It's because the origin of life seemed to have gotten started very quickly after the Earth was cool enough to retain its volatiles. This is a little clock. In large numbers are the billions of years from today. We're at the top, humans, mammals, plants, and this is the time when they found various fossils that indicate signs of life. And you'll see there are people who claim that there are fossilized bacteria 3.8 billion years ago. So that means when the Earth was formed some 4.5 billion years ago, it was a very violent place for a long time. Lots of comets coming in, lots of asteroids, terrible place. Within a few 100 million years, apparently, this kind of complex chemistry started in, leading to life as we know it. It's a very short amount of time. So something's going on that no one really, we do not understand at all yet. So this is the kind of picture, a nice comet comes in, the ices, these are the so-called amphiphilic molecules. They start floating around, they coalesce and start to produce these little vesicles. Inside, this is what it would look molecularly. This is the tails and the polar heads. You need to have something that helps get things across the membranes. That's where these types of characters come in. You need something to capture light, drive reaction. So it's quite an interesting array of things. And so I want to summarize this part, and then we're going to go to tomorrow. And then we'll be done. And tomorrow is very short. So to summarize what you've heard so far, the ready abiotic synthesis of all these kinds of molecules, and you can read for yourself, in realistic cosmic ice simulations, and that's what these are. We match things very well. Implies that these kinds of compounds are widespread throughout the cosmos, certainly in dense clouds, and available to habitable planets. So if conditions are right, that means the planet is in the right place, water is liquid, and all of this stuff. And biochemistry is an extreme chemical complexity. That's a big and. This is a whole field. Many of you might end up in it in a few years, of emergence, complexity, the emergence of complex behavior from systems. It's the new. So all of science has come to a point now where we have answered a lot of questions, but there are enormous questions starting to emerge. And the normal tools of science are really not capable of handling them, in my opinion, and it's just getting worse. This happened about a century ago with quantum mechanics, and I think we're at the same point. The conclusion you have to come to is that the universe is poised, or at least the ingredients are there, for life everywhere as far as we know. So that's where I'd like to stop there and now change a little bit to look forward. Any questions at this point? No? Okay. So we go to tomorrow. I've said all this, and it sounds very exciting and interesting, but for the fact of the matter is, you can shake these all up just like a bag of Legos as long as you want, and you don't get anything that looks like that. No one. This is a chasm that is enormous, and there are some people who claim that they've made life in a test tube, but they're I would say they're lying, but it's not quite straight. You can, yes, make simple chemical reactions go on, and so if you feed it the right stuff, fine. It's a cold chemical. Anyway, so in order to try to understand what kinds of reactions can take place, well, let's take our favorite friends, PAHs, and we focused on the chemistry in water because we know from Dick Zayer's experiments here what the final product is, but we can't use infrared to monitor what's going on with the pHs in water ice. So what we can do is use the visible, and color is our friend here. This is this particular PAH, frozen in water ice. The absorption spectrum is the dotted line above. It absorbs around 350 nanometers. Now we're back in the UV. And that's all that, it's a clear, just looks like water ice. There's no absorption out there where you see those lines at 400 and further. This is about where your eyes start to pick up. Purple is here, blue, green. So this is not color. Once you irradiate it, the neutral molecule disappears, and we thought all of these other products would start to show up. Well, no, they don't show up. All of a sudden, we get an absorption here, and Murthy would look in the literature. This is the ion, so I'm positive. It's the positive, it's the cation, it's positive. It's this particular pH having lost an electron. Now, okay, big deal. Well, the big deal is you would have expected 1 million fragments, but again, these pHs are such strong, stable molecules. Even in under these conditions, they keep their identity. They'd rather lose an electron than break a bond. Now, so then the next question is, this was at 15 Kelvin. How stable are they? Well, they're very stable. Murthy started warming. This is now with a larger pH, this character here. Here's where the neutral absorbs. Now we're in the visible, the red, 600 or, yeah, now we're in the, yeah, 600 nanometers to 900 nanometers. So 600 is this, 6 to 700. This is the other limit of visual sensitivity. This is red, near infrared. So when you have this strong material, it absorbs the red, so the ice looks blue. The red is taken away, it looks blue-green actually. When you start to irradiate it, the ice gets, the color goes away, and we get the ion absorption way out here that you cannot see. The solid line is the spectrum at 20 Kelvin. Murphy warmed it up, degree, a few hours, not a degree a day. We wanted to see how stable these things were. Well, these things sit out there for years. He warmed it up to 10, 20, 30, 40 degrees. Then he jumped to 2 or 3 degrees a day. He warmed this thing up for over a month and a half. Finally, at 120 degrees, it started to get a little weaker. Now, 120 degrees are solar system temperatures. So if your ice is beyond Jupiter is something like 90 degrees. So if you're up beyond Jupiter, you're much colder. So any ice in the solar system, now we're now no longer in the interstellar regime, these results are relevant for that as well. And as I said earlier, some 30 tons of interplanetary dust particles are falling on the Earth every few months. The interplanetary dust particles contain these PAHs. So everything out there should have a little dusting of this material. It's exposed to solar radiation. We also found that these things, when they are in ice, the ionization energy is lowered by 2 electron volts. So normally, you need a lamp with higher energy than this little fluorescent lamp I used to ionize to pop an electron off. You can use visual light to ionize these things. So suddenly there's a whole regime that was completely unexpected, what's driving the chemistry in these ices, opened up and it's completely unexpected. So what we found, you don't really get those products, that juglone, that aloe kind of compounds or whatever, until you're almost at 150, 200 degrees. So it may be that there are a lot of these things all over, and we're even wondering if they might play a role in atmospheric chemistry. Clouds are not this cold, but there are lots of PAHs in the atmosphere, and there's ice, water ice in the clouds. So let's go back now and look at some of these colors. And now it gets simple, so you won't have to wreck your brains much. Remember this goop? But there's that ice. Now remember the color of that ice that has not yet evaporated. And after having listened to what I've just said, notice the colors here. Could it be that these colors on these planets, and these icy planets, icy moons, are really arising from trapped organics? Most solar system folks prefer sulfates and minerals and really rocks. But the fact that you see these cracks, it's unusual. Here's another similar comparison. Here's another residue where you see the brown and goldish brown a little more strongly. What's happening? Okay. This is the Europa. Oh, let's go back. Jupiter's moon Europa. Now we're a little closer than Saturn. And Europa's got a lot of interest. This is also a planet, a moon that's covered with kilometers of ice, so these cracks have fascinated people. But notice these colors. So one question is, do residues in trapped organics contribute to those colors? The colors you just saw are very similar. Or do these things be arising from actual biological activity? And that would come to the question of a biomarker. What is a biomarker? We're going to send spacecraft out to these places to look around for things. A biomarker is something that a living system moves around as it's alive, or once it's dead. You can only make these kinds of compounds through a living process. And here again, probably most of you in the room, not all of us, but between 8 and 10, this made big news. This was a little meteorite that came from Mars. It was found in the Antarctic in the early 90s, I believe. And it caused quite a stir in 96 because there was a wonderful paper that there was even it created such excitement that there was even a meeting at the White House. What is the implications? Does this mean there's life elsewhere in the solar system? One of the lines of evidence was these pictures of things that looked like real worms. Now, biologists on Earth say these things are too small. There's a huge controversy about this. But one of the other lines of evidence was this rock was supposed to have biomarkers, signs of life, residues from a past life. And I was all excited until I saw the paper, and what those organic molecules were PAHs. We know they're all over now, right? So I don't consider them as a serious biomarker. They, in context, maybe. So our role for many years was the role of the party pooper at these meetings. Many astrobiology meetings, where these people talk about this biomarker and that biomarker. We can make almost all of these things abiotically. So we were very unpopular, never got invited, but they're coming around because, unfortunately, if you really want to address this seriously, you need to know this. It's very complicated, and it's going to be very, very difficult to sort all this out. So that's really the future. I think separating true from false biomarkers is going to be a real challenge for a lot of these machines. And robotic exploration is probably the way to go. So what I'd like to do is summarize now just, this is the large view of where we've been. And again, put it in the context of where I started, where OH, CO, and ammonia are big news. Now we're talking about polycyclic aromatic hydrocarbons, and I say shockingly large molecules by interstellar standards, and I mean it. In cold clouds, where planets and stars are forming, we know the composition of the ices, and we know how that might play a role upon ultraviolet light irradiation to produce these nice compounds. And comets and meteorites see primordial planets with all of these ingredients, and they certainly take part in the budding chemistry on these young worlds. So with that, I'd like to say, and of course this work doesn't get done by oneself. There's a large group of people over the years here and all over the place. And we have physicists, mathematicians, astronomers, chemists, and theoreticians in this picture. And now we're on a new wave. Most of these folks are elsewhere. Good jobs. JPL, Goddard universities. And these are some of the names. We work very closely with the group here at Stanford, Professor Zayer's group, on the analysis of small things, and lots of it. And then I'd like to leave you with the arrays of power structures in our database. So thank you.
This is the perfect time to ask Dr. Amendola any questions you have, and if you're embarrassed, ask in front of the class, like, I didn't really get spectroscopy or whatever, I am sure that he would be happy to explain it to you. You got to remember, someone like me, Avi and I have sat through this 3 or 4 times, so we have a head start on you. But I know there are people in the room who haven't had a huge amount of chemistry, and you shouldn't feel awkward because you're not going to get it anywhere else. I don't think the book really covers this kind of stuff.
A couple of the articles on.
What about the next step? What about getting it, higher and higher temperature?
Well, we'll go higher. We'll go to room temperature. And we find the thing goes down. It actually just doesn't go away in a flash. When Raytheon's able to measure it, you'll see the ion go down in the case of naphthalene, and at the same time the naphthalene with the OH on it there starts to grow. So it's somehow that ionized pH, there's enough force there that it's tearing the water apart as it can move around as the ice softens, and that's what's driving the chemistry. But it goes away slowly. That 100, that's a very large pH, the 120 Kelvin, and there was evidence for that up to 150 Kelvin. It goes slowly, disappears, but it doesn't all go in one big bang. Does that answer? And then what's left are these other things, which then we take over here to Stanford and predict in this game with the sensitive analysis. Does that answer the question?
We don't have the next step in what happens. I mean, basically, we get to a point where we can see how these carbon compounds are formulated on ice particles. But the next step, where it actually takes another level of complexity,
No,
It's not modeled
no.
in.
That's just what we're starting. Some theoreticians are working on it. It's very complex, even with the latest computer theories. It's at the edge of that, the frontier of that field.
It's not the same question to ask, like, what's the first biotic process? You're talking about everything that, all the chemicals that you have were abiotic, but what makes it, what's the step that makes it biotic? Is that the same question?
That's a good question. And if we really, that is the question. When does chemistry go from abiotic to biotic? And I don't know if we'd even recognize it yet. I mean, making these little vesicles, it's a step, obviously, but these are a far cry from the kinds of things in our bodies or in the flowers. They're much more sophisticated molecules, we think. You don't even know what these are. We're working, but the amounts are so small.
We'll talk a little bit about what it's
Yeah,
like next
I think
week.
the rest of your series actually deals with this question. But it's a long ways from getting all of these things. I remember years ago, what was it, Fred Hoyle had the analogy. Imagine all the parts of a 737 were just laying on the ground, and a hurricane flew by, and suddenly there was this airplane. He said, that's much more probable than throwing these compounds in a bag and having something alive come out of it. So we're really we've learned a lot, and I come back to what I was saying earlier. We've learned a lot, but I think there are some really profound questions, and I don't know if we have the tools to answer them yet. We're not looking at some of these things right now. Look at cosmology. I don't know how many of you even pay attention to this, but now we're talking about 97% of the known universe is dark matter and dark energy. What is that? I mean, physicists think they have all the secrets. So. Anybody else?
I have just a, go ahead.
What's the stuff in the bottle?
Oh, this is a pH called benzoapyrene. So what is that? Oh, well, use a chalkboard. I haven't done this in a long time. Pyrene is this. Benzoate has got another benzene ring on it, either here, and I'm forgetting it's either here or here. I'm not sure which one it is. But it's not a good one from the cancer perspective. That's why the bottom is sealed, and it's sealed with, it's a great fluorescer, but it's in cigarettes, it's in everything. I mean, you'll get it out, so you go outside, car exhaust, diesels, it's all over, soot from chimneys. But it's a pretty aggressive carcinogen.
No, but I love the Tide Box demo. That's
Yeah, no.
that's
I walked in the garage the other day. I turned the lamp on, and my eyes popped out of my head. The things that lit up, I didn't expect. I imagine if you go to a supermarket in the dark with one of these lamps, it would be a hard trip.
That'd be fun to filter to the supermarket in the dark.
Yeah, and then try to figure out what's in it. What is the dye? Because most of the dyes are based on these aromatic structures. You just add little things to them to move them around.
Is there another question?
There's a gap between the DNA and these
Yes.
vesicles or wherever.
Oh, yes, sure.
And your field is to grow towards the DNA from the
Well, I don't
this
think
side.
we'll ever make it. Next week's lecture, maybe.
Yeah, well, say that's the direction. What grows from the other end? Can you start taking apart the existing living ones to try to turn them more into these simple ones and see if they'll still, fly the 747? Like, can you take them apart from the other side?
When does it still have
Can you
all
go
this function?
abiotic from biotic, starting with the simplest
I think that's
replicators?
what you'll hear. Andrew is trying to, the amino acids are the building blocks of proteins. Now, I'm a chemist, so what I say now, take it with a grain of salt. And it's the proteins and the enzymes that are made of amino acids that do all these functions. Take things apart, put them together, tear food apart, put these molecules here so your body can use them. What I think Andrew is doing now in that field, not just Andrew, but people in that field are saying, how many amino acids do you need to get some simple functions of this other sort? So they're taking it from the other end. They're taking, here's the big old protein, taking it apart, I guess, I don't know, and then finding when it no longer works.
I know they've done some work with mycoplasma genitalium, I believe, and taking out genes. It's got the tiniest genome of any organism. You know, how many things can you take away, like your 747, and it will still fly before it crashes?
Right, the dream is some kind of like nothing but glycine, but it is replicating. You know?
That's, I don't think that's going to happen.
Well, I've been sort of, half joking the last couple of years and saying, look, it seems like it ought to be such a small step between the sort of molecules that you're able to produce in the lab and life. A much greater step should be between a bacterium and a dinosaur or us, but in fact, that's a much tinier step. And so it always makes me wonder, is it really because it's so difficult, or is it, life apparently arose very quickly as soon as the conditions were fine on the early Earth, and yet it took billions of years before, Stanford was built. Is it because there's just something stupid we don't know, like it has to be done in the full moon, or you stir in an eye of newt, or, something? Is there going to be some announcement, tomorrow even, and we say, of course, we forgot that, and I'll tell you, all right, instead of a term paper, everyone's going to create life, I'll give you test tubes Thursday and bring me something next Tuesday, and you'll say, that was a whole lot easier than writing a term paper. So, it's sort of in the air, and maybe it'll turn out to be something really dumb and stupid, and maybe it'll continue to be this insurmountable gap that we haven't figured out yet.
Now, I heard Stanley Miller, who Lynn mentioned, he did this experiment in the 50s, I guess, where they made these kinds of compounds, but under a simulated early Earth atmosphere. And I heard him say not too long ago that in those days we thought in 10 or 15 years we'd really understand how these things came together and they started to function as simple living things. I said, all of us from those days just had no idea then, and we still don't understand why it is so difficult. So there's something we're all missing. And this is not my game, but there's some very basic stuff that's...
And maybe one of you will be the person to solve it.
That's tomorrow.
Your question?
I just have a question. So we've heard a couple times now that the universe is mostly hydrogen, there's some helium in there, and now we've been hearing about more complex molecules, but how deep is our understanding of where hydrogen comes from? How?
Hydrogen is thought, well, the answer is it was made in the Big Bang. And that's what you're seeing is the relic from the Big Bang, hydrogen and deuterium, and some lithium, and maybe even boron.
I've seen it some places and not others.
Yeah.
Helium.
And that's what's thought to have been made, and then it's from that process of coming together and forming stars that the other elements were made. And so when I showed that periodic chart, I imagine that if this current model is correct, in some billions of years, the box for hydrogen will be smaller and those others will be bigger. That's the story.
So there's a model for how first atom formed?
Yeah, these are the Big Bang cosmologists, but again, these are the same characters who will tell you 97% of the universe does not matter. So,
in other words, email Seth back and get marked.
I used to believe this a lot more 10 years ago. What is believed in?
Yeah, I think what she's getting at too is that after the Big Bang, the idea is that as it was cooling, you could form things like electrons, and you could form protons, and you could ultimately form hydrogen. That hydrogen was not there from time to time. Seth got us back to 10 to the minus 43rd of a second.
Yes, yeah.
But even after a few seconds, there's no hydrogen. It's something that happens slowly during the cooling. Is that your question?
Yeah.
Any other sort of more general questions? Again, I think that Lou would be happy to answer any questions privately, and don't be too embarrassed to ask any question whatsoever about this, because again, a lot of it is not in the book, and I want you to understand what he told you.
It's pretty profound, but you have to think about it. It's exactly what you thought. What did I just
Stunning.
do?
Absolutely stunning. That's, I love listening to this lecture. All right, in that case, let's thank him very much. Andrew Cora up on Thursday, and no doubt a few of you will be joining in the festivities, and then we'll move on to real life next week.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.